we do this another type of flow. So, we covered passive scalar, now we will cover stably stratified flows. So, I will define what that is, and which is very important for atmospheric applications. So, stably stratified turbulence. So, the configuration is the following. So, we have dense fluid sitting at the bottom, of course, there is gravity. So, passive scalar we had no gravity, okay, but now we have gravity which will add force at every scale. So, rho g, density times acceleration of the acceleration due to gravity, and light fluid above. So, in Earth atmosphere, no, so if a fluid is heavy at the bottom and it decreases, the density decreases when you go up. So, we assume that density is decreasing linearly, the mean density with height, you see it is the linear profile. So, the rho bottom at the bottom level and rho top at the top level, but it is linear decrease. So, it is true only for small patches of fluid, it is not true for full 10 kilometer of Earth's atmosphere. You take small patch, you can apply this theory. So, what is the equation for this? Okay. Equation is very similar to what we derived for scalar field, now with slight modification. So, I am just going to show you the equation with the PPT. So, these are, everybody knows this, the pressure gradient, viscous term. This Fu is external force, which actually I should write Fu external, but gravity force is here. So, I divide by rho m, no. So, rho g is the gravity force. So, fluid density itself is coupling, no, there is a fluid, its density couples with gravity, Newton gravity, rho g, okay, and gravity is in down direction and z is up, this is my z direction. So, its minus sign is coming because of that, okay, straightforward. But this works at all scales, because density is acting at all scales, right. There is a in Fourier transforms, okay. So, you see density will have spectrum, but it is there at all scale. So, this is unlike Kolmogorov theory where force was assumed to be at large scale. Now, we have situation when force acts at all scale, and that could affect your scaling, means spectrum or flux. Is the motivation clear? I mean, that is what we will study in today's lecture. Now, what about density equation? So, very similar to the last passive scalar, except now I must write that total density is written as the following. So, I should have written that, read rho total. So, in fact, in my notes I write this rho as total rho. Now, this is written as some symbol, math class symbol, is rho bar z, this rho bar z plus density fluctuation. So, this is a fluctuation over this linear drop. So, this one is 0 on the average, is that clear? So, that is a notation. So, you take the mean, but mean is not constant mean throughout the fluid, it is a rho bar of z, okay. So, that makes the equation bit understandable and also simulations is bit easier. So, this is rho total, you can call it rho total, is rho bar z plus rho fluctuation. So, my equation basically should be for rho total by dt plus u dot grad rho total equal to kappa grad square rho total, right. This is what we wrote last time. This density is like mass conservation, but while doing mass conservation there is a flux term plus diffusion term, okay. So, this we did for the scalar. I would recommend that you please try to derive it yourself, okay. Now, rho total has two parts, rho bar z and rho fluctuation. So, if I put this here, so what will I get? What will come from rho bar z? So, it is changing along z direction. So, it will be u z d by dz, other things will be 0, d by dz of rho bar z, one term, other term will be u dot grad rho. So, this is the second term, and this is the first term which has gone to the other side with a negative sign. Okay. And of course, rho bar z has no time dependence, so this is basically rho fluctuation, and this is also rho fluctuation. Okay. So, this equation for rho fluctuation, fine. So, if for the rho fluctuation we have a source, there is a force term f of rho, right. So, I have got in difference to passive scalar which was rho fluctuation everywhere, but it had basically f rho at large scale. Now, what about this force? Will it be active at large scale or every scale? So, d rho by dz is constant, but uz is there everywhere at all scales. So, these two forces are active at all scales, and that is going to change our physics. Fine. Now, all our formulas which we did in the last class on scalar flux, scalar mode to mode, they will be applicable here as well or no? Because all the mode to mode transfer, flux, shell to shell, they all depend on the structure of the nonlinear term. The structure remains the same. So, all the formulas for the flux will be the same. Okay. So, there is no change, except how the flux change with k, that will be coming from this k dependent stuff. Okay. So, before we go on, so we need to see what does this force do. There are two forces, Fu and F rho. Now, if we call this mathematical, so Fu is, in fact, F is a buoyancy which has a physical interpretation, is rho g. So, okay. So, by the way, so rho fluctuation times g, rho z part can be absorbed in pressure. Now, that easily you can do, but I will just save my time and I will not tell you exactly. So, my buoyancy is written as rho g, and rho is a fluctuation. The rho mean part, which is rho bar z, is absorbed in pressure with some small algebra. So, this is the fluctuation part, this part which was there in the previous slide. So, I want to see whether this buoyancy is giving energy to kinetic or taking energy from kinetic, that is the key part. Okay. So, there is a force. Can we say something about the sign of injection of kinetic energy? Okay. So, to understand whether kinetic energy gains from buoyancy or not, we need to analyze the linearized equation. Now, I will tell you the result. So, linearized here is that I drop the nonlinear term and the diffusion and dissipation term. So, this equation will give you wave solution, okay, and it is a very important name, is called and this you can see in my book on buoyancy. Okay. So, this is derived in Fourier space, in fact using Kriya-Haring basis. So, what is gravity wave? Gravity wave is in the ocean surface or water surface, we have fluid going up and down, and it moves, right. I mean, the waves, if you just put a drop of not one stone, then wave, this gravity wave on the surface it moves. So, that is called surface gravity wave. What is internal gravity wave? Is inside the fluid. So, inside the lake you go inside and do some disturbance, inside the water there is a wave which propagates, that is why it is called internal gravity. Okay. And these waves also travel, and they travel with a frequency, okay, and that is called Brunt-Weisseler frequency, okay, and that depends on this d rho by dz. So, it depends on these properties. So, I can write down what is Brunt-Weisseler frequency. So, n is square root g by rho m. So, I will just put it here. It is a frequency which is square root g by rho m mean d rho by dz. So, it has very similar properties gravity wave, but it is inside the fluid. Okay. Now, so we can write down the solution which I have in my notes. So, u bar is cos kx minus kx x minus nt. So, if I look at in the fluid, so if my k is along that direction, kx direction, so the fluid will be going up and down. So, the fluctuation is perpendicular to k, because it must be, right, k dot uk is 0 and it is just going up and down. And also, so if you move, it will also, the wave will move in one direction. So, there is a group velocity, there is phase velocity. So, this discussion we really do not need it for our discussion, but these are wave solutions. And we can also write down what is rho fluctuation. Okay. So, because of this relation, rho will be sine function, and this is amplitude. So, what about rho times u bar average? Cos and sine will be, if average over the full, either in time or in space or both, is 0. So, what does rho times u bar give you? What is the meaning of this? So, our force is of this form, right? This is Fz, or this is a force by buoyancy. I call it Fb, B for buoyancy. So, Fb dot u, what is it? Fb dot u. So, I change the color of the pen. Fb dot u is a force supply rate by buoyancy, that is apart from constant, there is a minus rho u z, correct. If I take the average, it will be that. So, rho u z gives you the direction. So, this in fact is u z, let us u z. So, rho u z is a injection, minus rho u z is the injection of energy, injection rate of kinetic energy to the system. It is 0 for waves. What does it mean? That on the average, it is sometimes taking, sometimes losing. It is like potential energy, no, kinetic to potential, but if you average over time, it has 0 net transfer. Okay. Now, what will happen if I put nonlinearity? Will the sign of this guy change? And what should it be? Should it be positive or should it be negative? Now, is my question clear? So, this is for, it is 0 for linear solution, but if I put nonlinearity, can you argue that what should be the sign of rho u z? Okay. So, I give my argument. Now, the system is stable, it is a wave solution, so system is stable. If I put viscosity, then in fact is just the waves will just die. System is this way, this is why it is called stably stratified system. By experience in the earth atmosphere, you do any perturbation, it will die by viscosity. If you have viscosity turned off, it will just be waves. So, in this system, if this is rho u z is positive, then so we need to write down the equation for the kinetic energy. So, let us write down the equation for the full nonlinear term. So, let us write down the equation for the full nonlinear term, nonlinear equation. So, it will be d u z by dt d u dot u. So, u squared by 2 plus the force nonlinear term n u dot u real. So, let us do in real space only, okay. And there is a buoyancy F b dot u and the pressure gradient minus grad p dot u, these are the terms, right, and viscous, I turn off the viscous term right now. So, this term, if it is positive, what will it do to the, so if I do the integral of the whole thing, this integral give you what, nu dot u, this integral gives you 0, we have done it before. For periodic boundary condition or vanishing boundary condition, nonlinear term does not give any net transfer, it is only exchange of energy among themselves. Pressure term is also 0, I can write as, I mean basically pressure does not participate in energy transfer. So, both these integral go to 0 integral, and dissipation will kill, but if I just turn off the dissipation, then if this is positive, then U squared will increase with time. So, they will make it unstable, right. U squared increasing with time is unstable. So, stability requires that this must be negative, stability condition. Since you are calling it stably stratified flow, it must be negative. So, we argue this way. So, my FB dot U is negative or minus rho UZ is negative, and rho UZ must be positive. So, this is an important ingredient. Are you happy with this? So, since the system is stable, if the buoyancy is supplied energy to the system, then it will increase the kinetic energy and will make the system unstable without viscosity. So, we want this sign to be, the energy injection rate must be negative. Okay. So, that is by definition of stably stratified flow. Okay. Now, if that is the case, then we have very good idea about the flux. Now, I am building this story for some direction. Will the flux increase with wave number or will it decrease with wave number? That is what I am after. Okay. So, this is the energy equation, right. So, this coming as a nonlinear term, this is the injection by buoyancy and this is the external, Fu is external. So, the external force in addition to buoyancy. So, since buoyancy is decreasing the kinetic energy, so if you want to maintain a steady state, then you need to supply at large scale. So, in earth, if you do not supply something coming from the ocean or some shaking up, it will just become quiet. In fact, the wind also will not move, you can't, this will be all quiet. So, this is external force, this one. So, for E rho, you can also derive these equations. Okay. So, I am skipping this part, the derivation, but E rho will be that, and it turns out we can also derive. So, I think we will focus on only one part. I will. So, we have variable energy flux, no. So, I am skipping the, so du by dt. So, let us steady state, what did we derive? This we have derived on many occasions. So, d pi u by dk is Fu of k minus du of k, or Fu right now I focus on the inertia range where is only the buoyancy part. So, external part is 0, inertia range here. So, F external is here, which is not active in the inertia range, and dissipation also not active. So, this is the in the equation of the flux in the inertia range. What about pi rho? Now, I am not telling you the details, but you can show that it comes with a negative sign, because it is just opposite, no. If you remember, u dot has rho and rho dot had uz. So, the dot product this with u and the dot product, well, I mean basically you get this. So, I will not prove it, okay, it is straightforward. If I sum these two, what will I get? So, if I add these two, what will I get? d by dk pi u plus pi rho is 0. So, pi u plus pi rho, these two fluxes add to give you 0. So, the time derivative, that means pi u plus pi rho must be constant. So, that is what I have written here, pi u plus pi rho is a constant, the key ingredient for stably stratified flows. So, these two fluxes give you constant. So, both of them change with k. Okay. So, because the buoyancy is active at all scales, it will change with k, but the sum must be constant. Now, how will they change? Can you make a guess? So, Fb is negative. I proved a sign, right? I mean, I hope you are convinced. So, Fb is negative. So, pi u should decrease with k naturally. So, flux will decrease with k, and pi rho should increase with k, because Fb is negative. So, pi rho should increase with k. So, that is great, and we can, well, this is what it is. So, pi u is decreasing and pi rho is, well, pi rho, there is some subtle reason why pi rho is increasing, but slowly. So, now I think I am going to skip some arguments, well, some more details. So, stability-certified flows come in three types. So, I will just write down quickly, maybe you should know this. So, I will just write down regime specificity. One regime is when gravity and nonlinearity both are equally strong. So, this rho g term and u dot grad u both are of the same order, okay, roughly equal, and this is called moderately stratified flow, moderate stratification. Okay. Second, if u dot grad u is much bigger than rho g, this is called weak stratification, or no, because gravity is weak, so weak stratification. And third is other way around, u dot grad u is much less than rho g, so it's strong stratification. Okay. This one you can make a guess, what should it be, what should be the property. Want to make a guess? Is weak, gravity is weak, so it's like fluid solution, Kolmogorov theory. Gravity is not doing much, some changes, but there are some initial gravity waves, but Kolmogorov theory works quite nicely. I will cover this one in this today's lecture, but this one is strong gravity, it becomes 2D, because gravity is too strong, flow moves easily in the horizontal direction, not so easily in vertical direction, and so this is called quasi 2D flow. So, in fact, Earth atmosphere is in this regime. Okay. So, this is a big topic which I will not discuss, but I will illustrate the dynamics with this moderate stratification. Now, there is a theory for moderate stratification. So, this for moderate stratification, and this theory was done by Bolgiano and Ubakov, 1959, okay, way back. So, according to their theory, which I will derive quickly, the flux will decrease with k, and decreases at k minus 4, k to the power minus 4 by 5. Why? Because this sink of, so this force is taking it away. It's like the analogy which I used to make is for financial system is corruption. So, there is some things are just taking your money flow, you know. So, this buoyancy force is taking it away, and where is it pushing? It is pushing into potential energy, and of course, finally it goes into heat. Okay. So, but so let us try to derive how to get minus 4 by 5 from scaling arguments, from dimensional analysis. Okay. So, I will quickly derive it. Okay. So, I equate the nonlinear term with gravity, but rho is function of k, right? Rho is active at all scales. So, it gives you k u k squared is g times, so g times rho of k, correct? G is constant, but the rest all are function of k. Now, you make another assumption, you take the flux argument. So, what did I write? Pi u plus pi rho is constant, right? I showed that. So, what will that give you? Pi u is, so it is like, you know, big system with fluid, and so pi u is u cube by L. So, in Fourier space is going to be k u k cube. We derived this, no, u cube by k. So, it comes from force which is k u k squared multiplied by u k from nonlinear term. Happy? Is local flux. This comes from Kolmogorov theory. Pi rho will be. So, what is the flux of pi rho? So, what is the nonlinear term of the pi rho? It is u dot grad rho multiplied by rho, no? So, that will be pi rho. So, rho k squared times k times uk. So, this must be constant. So, I will make it equal. Okay. So, if how do I solve this equation now? So, by the way, so I must make a remark that Bolzano and Dubokov dropped this term. They dropped this term and solved the equation. So, let us quickly solve that equation what Bolzano and Dubokov did. So, they said, well, pi u will be small. So, pi rho equal to constant. So, there is an assumption. In fact, we looked at this assumption and we got some nice result. Okay. So, let us assume that pi this you can drop the kinetic energy flux. This is what I have shown here. Kinetic energy flux is decreasing like this by more refined theory, and pi u increases and becomes a constant. This is done by Shadab, who is who has gone home today. So, he did this simulation with some interesting work which I am going to show you after this. So, if I just keep this rho k squared uk, now I just substitute rho k from here. So, what will I get? K uk and rho k squared will be, I will forget g. So, to make my life simple. So, it is going to be k squared uk 4, correct? That equal to constant, in fact is pi rho, correct? This total flux pi, this constant is total flux in fact. So, what does it give you? What uk? uk 5. So, it's k minus 3 by 5, not minus 1 by 3 for Kolmogorov. If you remember, it was 5/3, no? So, yeah, minus 1/3. What about spectrum now? So, EU of k will be what? uk squared by k, right? That is the definition of a spectrum. So, k minus 6 by 5 minus 1 is minus 11 by 5. So, spectrum is not 5 by 3, it is 11 by 5. That is spectrum for stably stratified flows kinetic energy. What about the flux? Kinetic energy flux now is small, but let us compute it. Pi u, which is k uk cube. So, what is ek cube? Is k minus 9 by 5, right? Is cube this. So, that gives you k minus 4 by 5. So, this is supposed to go down as k to the power minus 4 by 5. This kinetic energy spectrum. I should put in red, but yeah, this is dropping quite rapidly as k minus 4 by 5. So, kinetic energy flux is not constant because energy is being sapped, kinetic energy is being sapped at every scale. Now, we can also compute E of rho of k. How will I get this? It is rho k squared by k. What is rho k squared? From here will be k squared uk 4 by k, right? This I am just following that. So, these things are very simple, you must do it yourself, and this k cancels. What is k uk 4? K minus 12 by 5. So, k minus 7 by 5. So, the density spectrum is k minus 7 by 5, not 5 by 3 like passive scalar. Okay. And you can easily check that pi rho of k, which will come from here, is k rho k squared uk is constant. Okay. So, what is the final upshot of all these arguments? Bolzano-Dubokov says that this Bolzano-Dubokov argument in 1959, kinetic energy decreases steeper means faster than minus 5/3. And why is it steeper? Because it is being sapped. So, some energy was supposed to flow which would have maintained 5/3, but somebody is already taking things at everywhere, like leakage in pipe. You know, there is a water is flowing in a pipe, but it is flowing in Fourier space. It is not in real space water pipe, it is Fourier space water, but there are holes everywhere. So, there is hole everywhere. So, water will keep decreasing when you go down and down. So, that is why flux, the flow is like water current, and that is decreasing with k. So, that decrease is k minus 4 by 5 and kinetic energy spectrum is minus 11 by 5. Okay. And similarly, the density is also affected, it is 7 by 5, this one. So, what we did recently, which with Shadab and there is a faculty in mechanical. So, we looked at the full equation. So, instead of making the assumption which, okay, so I want to make one more break. So, after this Bolzhunov-Nabokov said, so this is this part Bolzhunov-Nabokov. So, they make a remark that the spectrum will go as minus 5 by 11 by 5 EU and k, then it will, this is their theory, they say it will become shallower, it become minus 5/3. Okay. So, I will stop. Thank you.